Welcome to the review. All of these questions will be very similar to what you'll see on the actual CBE. So if you have any questions, then we can go over anything in more detail. If we're going too quick, anything like that, just let us know. My name's Marissa. I teach 1050 for the professors Caitlin Clausen.
My name's Sam. I'm a recitation leader for Jace Ritchie.
I didn't mean I teach. I'm also a recitation leader. Okay, yeah, we'll just get started.
One thing to note, this will go on YouTube, so just your faces won't be shown at all, but yeah.
Oh, yes, thanks. Yeah, and if you don't want to talk, if you don't want your voice on it, then you don't have to talk. It's fine. Okay, so the CBE 3 is going to be covering all of these different subjects. We've got quadratic functions, polynomials and their graphs, polynomial division, real zeros of a polynomial, fundamental theorem of algebra, and rational functions and their graphs. So we'll be going in all of those, breaking it down. First up is quadratic functions. Quadratic functions always have some x squared term in it. So that's the only thing that makes it that. It's just x squared. In other words, it's a parabola, as we're used to seeing. The function can be expressed in different but equivalent forms. So these three forms are very, these are important to memorize, okay? So all of these ones tell us different things. This first one, a of x minus h squared plus k, does anyone know what kind of thing what situation you might use that one for? Maybe what are you given, or what do you need to find?
If you need to find A.
Yeah, exactly. So A is usually that unknown, and what you're usually given is the vertex. So if they give you anything with the vertex, then that's how you know you want to use that one. Vertex is in the form of HK. So if they give you vertex, you can plug the HK in, and then they'll usually give you another point as well to plug in for X and Y. And then that's when you have K, because that's when you find A, because A would be your last unknown. But we'll do an example of that. That's just explaining that one. Okay, what about this second one? What form, or what are you given? What is that one telling you? That one is telling you the zeros, okay? So if you're factoring it down, then this is like your fully factored form, and it's going to be telling you the zeros, and in other words, zeros are also your x-intercepts. So that tells you the zeros, and then this last one is just kind of your classic polynomial, quadratic form, and that one will tell you your y-intercept. Or all of them can tell you your y-intercept, but this one's kind of your go-to because you just plug x equals 0 in, and then it just cancels out all the terms and sees your y-intercept. So that one kind of just makes it a little bit quicker to find it. Sorry, I started writing smaller and smaller. Okay, perfect. Any questions with those? Okay, no matter what form it is in, they're all the same. They just tell you different, you'll just use them in different situations. So let's do an example of that. Determine the exact coordinates for the vertex and the exact coordinates for the x-intercepts of the parabola defined by the function. Okay, so what do those keywords, what it's asking for, what form are we probably going to be using? Or maybe forms. Yeah, that first one with the H and K. Okay, so, yeah, so we want to, let's see, put it in that sort of a form. What would be our first step, possibly? We've got some fractions. A lot of the time, if there's a coefficient in front of all of them, you could try to factor something out to have the 1 in front of it. So I would maybe take out the 2/3, because then it would just leave us with a little bit of a nicer polynomial without as many fractions. So first step, we can take out the 2/3, and we've got x squared. If we take 2/3 out of 4/3, we've just got 2. x. And if we can take 2/3 out of 5/6, I'm just going to do it over here so that we all kind of remember how to do it. 5/6, and then we're dividing 2/3 out of it. So we're going to multiply by 3/2. And that would be 15/12, which can reduce to divided by 3 5/4. Okay, so I want to check if I'm... Okay. Now we have this form, and we would want to, I'm kind of doing it a different order. I'm doing the y-intercept first on accident, but it's asking for both, so we can do the y-intercept first. So what are the exact coordinates for the y-intercepts? From this point, we want to change it to the second form, the second equation that we started with, and that one is just factoring it down. So how would we factor this one? Or is there an easy way to factor it? If by just looking at it, do you have like a go-to, oh, these are the ones? Probably not, especially with fractions, and it probably wouldn't give that to you. So that means you'd have to do the quadratic formula. And doing the quadratic formula, then you can do x equals, and then opposite b, or do you guys all remember the quadratic formula? Should I write it again? Okay, we got it. We'll do opposite b, so -2 plus or minus the square root of b squared minus 4ac all over 2a, so 2. Okay, that inside the square root can reduce to 4 minus, and then 4 times 5/4 is just going to be 5 because those 4's cancel out. So it'd be 4 minus 5 over 2. Okay, 4 minus 5 is -1. Oops. There we go. -1. So -1 is also just I, right? So we'll just write an I there over 2. Whenever you have any sort of an I for your 0, then it's an imaginary 0, right? It won't show up on the graph. So this tells you that your two x-intercepts are both imaginary, so you don't actually have any x-intercepts, okay? Your x-intercepts have to be like an actual number that we're used to. These imaginary ones tell us that so there are no x-intercepts. Okay. Now for the vertex, do you guys remember the short little equation that you use for vertex every time? Dude, you said yeah?
Isn't it the first one?
Yeah. So we're going to use that first, or that would be if you're given the vertex and you want to use it. There's a different equation, and I'll write that down. It's -b over 2a. So maybe you recognize that one. It was a couple weeks ago, but that one, when you see, okay, you want to find the vertex, it's just -b over 2a, okay? So we can go to the original equation, and we can take -b, so we'd have -4/3 over 2a, so 2 times 2/3. Sorry, am I writing too small? Or does it work? Okay. Yeah, so -b over 2a, and that would be 2 times 2/3. And then we can just simplify that down. So this is just working with some fractions, so we want to be careful. This is where a lot of mistakes come, I feel like. Times 2 times 2/3 is divided by 4/3. And now we've got -4/3 divided by 4/3. So one thing divided by the exact same thing, but a negative is just going to be -1, right? Because you can just take that negative out. Oh my, I don't know why it's changing. There we go. Okay, so our vertex equation said -b over 2a is -1. And now that we have that -1, that's our x value for the vertex, and you just want to plug that into the original. So we're going to take our f of -1, and we're going to plug -1 in for all of our x's. Squared -1 plus 5, 6. And if we simplify that, we'd get 2/3 minus 4/3 plus 5, 6. And that, I'm just going to change them all to have 6 in the denominator. So we'll have 4 6 minus 8 6 plus 5 6. 4 minus 8 is -4 plus 5 is 1 6. Perfect. So we had our -1 from negative b over 2a, plug that in, and we've got 1 6. So our vertex is -1 1 6. That would be our vertex. Okay, and then kind of covered the solution, but that would be the solution for the vertex, and then there are no x-intercepts. And if you want to think about this parabola, right, if you're shifting it up, then it's 5 6 is your y-intercept, right? So on your graph, it doesn't start until 5 6, and it goes up, straight up. And so there's not going to be any x-intercepts because it doesn't touch the x-axis at all, okay? So that would just be kind of visualizing it. Or if you're ever unsure, then you can just always graph a bunch of random points, okay? Any questions with that? Okay, I'm going to probably go a little bit faster, but determine equation for the parabola that has a vertex at the point that and contains the point that. So this is the one that we would be using the first equation, okay? So it's given us a vertex and a point, so we're going to use the first equation. First equation, I'll write it up here, y equals a, and then we've got x minus h squared minus k, or plus k. Does that look right? Plus k. It might be minus k.
That's plus k.
It is plus k. Okay, perfect. Okay, so that is all of those. And then right here, we're given 4 out of those 5 unknowns. So they did that purposefully so that we can just kind of plug each of those in. So this point, since it's the vertex, then it will be in HK. And then this point is just XY, same as normal. So I'm going to take H, K, X, and Y, and I'm just going to plug them all in. Y is -1 equals A. X is 5 minus 3 squared plus 4. Sweet. Now I will just solve it. We're just going to solve for A. So 5 minus 3 is 2 squared. And then I'm going to bring that 4 over, minus 4 minus 4. We've got -5 equals A times 2 squared. 2 squared is 4, so we've got 4, I don't know, I brought the A to the other side. So we've got A times 4 equals -5, and we'll divide them both by 4. And we've got A equals -5/4. Okay, now that we found that unknown, then we can just write the equation in general. So yes, it contains that point, but we want the equation for any point. So we're going to do this exact same thing, but leave out x and y and keep those as x and y. So we've got y equals -5/4 x, and then the h and k we still plug in, -3 plus 4, and this would be squared. Okay, any questions with that one? Perfect. I'll leave that out just for a sec. Yeah, so you just find your A, and then you plug all your unknowns in. Solution, -5/4 x minus 3 squared plus 4. Got it. Okay, problem 2. Determine the y-coordinate for the point where the parabola intersects the y-axis. So, well, all that's asking, bunch of words, we're just looking for the y-intercept, okay? Where is the y-intercept? And I knew that because y coordinate for the point where the parabola intersects the y-axis. So it's just intersecting that y. So I'm just going to take this equation and I'm going to write it over here so we can remember it. 5/4 x minus 3 squared plus 4, I believe. Okay, sweet. And then for the y-intercept, what equals 0 in it? Where do you plug in the 0? Yes, good. So y-intercept is when x equals 0. So we're going to say x equals 0 at y equals negative 5/4 0 minus 3 squared plus 4. So we just basically took that x out, made it into a 0. Negative 3 squared is 9 times negative 5/4 plus 4. 9 times negative 5/4 is going to be negative 45/4 plus 4. And 4 I'm going to change to 16/4, just because we're working with fractions. Negative 45 plus 16 is 29. Okay, so I just took the 45 and I subtracted 16 from it. We've got negative 29, though, over 4. So that tells us when x equals 0, y is negative 29/4. Okay. Oh, they just asked for the y coordinate, so well, we got the same thing. Perfect. Okay, polynomials and their graphs. What's a polynomial? Any function that can be written in that form. So we've got a to the n is your leading coefficient. This form kind of might look intimidating, but you just can break it down into all the different things that you do know. So leading term is an x to the n. That and that is the exact same thing, okay? The leading term is exactly what it sounds like, the first term. The constant is going to be over here. Maybe I'll do like a little squiggly or something. Constant is over here. And leading coefficient is that first one. Once again, the leading coefficient. And degree of the polynomial is down there, that n, the small n. Okay, the leading term can tell you things about the entire behavior of the graph. The leading coefficient usually is what it's being multiplied by. The constant over here, that your go-to, tells you the y-intercept, other things too, and then the degree of the polynomial, that one tells you a bunch of different things. But we'll get into that, what it can tell you. Zeros of a polynomial. So if f of c, and c is just any number, any constant, if f of any number equals 0, then c is said to be a 0 of the function, okay? If x minus c is a factor of f, then it, meaning it divides evenly, then c must be a 0 of f. I'm just going to see how I wrote any of this. And if c is a 0 of f, then x minus c must be a factor of f. So all I wrote is c is a 0 right here. And that's the exact same thing as x minus c is a factor. So either way, those go hand in hand. They mean the same thing. Okay. Multiplicity. If x minus c to the power of n is a factor, then c is a 0 with multiplicity of n. So multiplicity, degree, same thing kind of thing there. What does a graph of different multiplicities look like? So these are like the parent graphs. Say we've got x to the, all of these are x to the n. If n equals 1, x to the 1, what would that graph look like?
Just a straight line.
Perfect, just a straight line. Okay, I'm just going to write it like that. X squared, we know that one. What's that? Yep, u parabola, like that. And then x cubed, this one is going to look like this. It's kind of like a little snake, a little bit. Okay, so those are the three parent graphs that you can kind of remember because of the different multiplicities. This is because if you've got a 0, let's say x minus, x minus 1. Okay, your 0 is at 1, and it has the degree of 2, then you know as soon as it touches, it's still going to be a 0, but that tells you that it bounces like a parabola, okay? So these ones, n equals 2 bounces. This one crosses. And then this one, not quite crosses, not quite bounces. It's kind of like a, how would we say that one? Any creative words that we can think of? Remember that one? It just,
It stops for a sec.
yeah, maybe halts. Stops for a sec, I don't know. Yeah, but it doesn't like just zoom through it and cross it really quick. It kind of, yeah, very slowly goes there. I'm gonna write halts, but you don't have to do that. But yeah, that tells you if you've got your 0 there and it has different multiplicities for the entire thing, then that's how you know which one is which and how they act around the x-axis, okay? Doesn't mean it's not a 0. They're all still zeros. They just act differently. Okay, the end behavior looks at the behavior when x values approach positive or negative infinity. So this is kind of a lot of different text, but I'll just summarize it. So as your graph gets bigger, either of those ways, then the end behavior is, where does the graph go? Does it go up there? Does it go towards the x-axis? Does it go down? Does it, yeah, just one of them, bigger or in either direction. To determine the right end behavior, so over there, sorry, I don't usually use an Apple Pencil. That doesn't look very well. To determine the right end behavior approaching positive infinity, determine if the leading term of the polynomial is positive or negative for large positive values of x. So I'm just gonna, this is how I kind of remember all of this information. Do a quick little table, and the table is super easy to fill out if you're like in the testing and you're like, what does end behavior mean? But all this is saying is you want to pay attention to the leading term, and if that's positive or negative, and then the degree. Where does it say degree? If we only look at the leading term. Okay, maybe not degree, but I'm going to write it right here. The table that I would use normally to remember all of this. So first is n is even. So if you have an even polynomial in general, or n is odd, and then we're going to say the leading term is positive or negative. So a sub n, that's what a sub n is, the leading term, is greater than 0, and then a sub n is less than 0. Okay, so these are the 4 cases we want to look at. If a sub n, if the leading term is greater than 0, so it's positive and n is even, that's just a normal parabola, right? X squared, 1 is even, 1 is greater than 0 and squared, or that 2 is even. So all that tells you is your 2n behavior are going up on both sides, okay? If it's negative, then that's just like a negative parabola. Then they're both going down, okay? So if it's even, then they're both going the same way, either up or down. If it's odd, then that would be like an x cubed function, okay? So the function that I just showed you before for x cubed, then it starts down and it goes up. So this one is going to be starts down, starts down and it goes up, and then if it's negative, then it's just the opposite of that. So it starts up and it goes down, okay? So this is kind of your end behavior. No matter how big your polynomial degree is, it could be in like 53. 53 is odd, so you already know, you already narrowed it down halfway, right? Okay, any questions with that one? Perfect. Sorry, I'm kind of doing this a mess. But choose the function from the following whose graph is shown. Assume A, B, C, and D are all positive real numbers. So it doesn't actually matter what the zeros of this are, it just matters that there are zeros. So we've got a 0 there, there, and there. Now what is the behavior at each of those zeros. What does the one right here, where it crosses, oh, how about I do colors? Where it crosses that at red, then what would the multiplicity be? 1, perfect. So I'm just going to say that one's an A, and that is 1. But real quick, if that's an A, then that would be a negative A. So this, the 0 would be x plus A, right? Because you want to do the opposite if you're solving for the 0. So x plus A to the 1. That's the red. Now for, let's do green. Green will do negative B, and that one is also crossing, right? So that one's going to be 1 as well. X plus B to the 1. Okay? And then lastly, for blue, what multiplicity is that one? What multiplicity is C? 2. Yeah, because it bounces. So we're going to go x minus C, because that's a positive C. You're going to do minus C squared. Now, if that's just me looking at it. Now, if we actually look at the choices, then we can see, here, I'll just do B, C, and D. So it's kind of the same thing. Last thing we have to look at is this A. Is that A positive or negative? Where does the end behavior go? Does both the end behavior go up and up or down and down? Down, yeah. So it's going to be one of those 3. We already know it's not F or R because those are both positive. And then we just look at these. T has x minus D to the 3rd. So that would be if it would go like that kind of a thing. And it doesn't. So we're not doing T. And then G and H, the only difference there is right there we've got x plus B and this one is x minus B. So it's going to be H, because you want to do the opposite of both of them, okay? So even though you do have 2 minuses, you don't want to do x minus B and x minus C. You want to do the opposite of all of it. Any questions with that one? Okay, so I did the zeros right here. Those are our zeros. Multiplicity when we did the 1, 1, and 2, and the end behavior when we figured out that it should be negative A. Perfect. 4, same thing. Now let's see, zeros, are the zeros negative or positive? How many negative ones do we have? Right here, we just have 1 negative. So I'm going to just go, I'm going to do B this time. I'm just going to go, we've got a negative B for a 0. And then we have 2 positive. So we've got a positive C and a positive D. Now the multiplicity, I'm doing this one in a different order, but we're all doing the exact same steps. Multiplicity, for B, what is the multiplicity of B? 2, perfect. So I'll just write it right below it. Multiplicity of C, right here where it just crosses, tells you 1. And D, another bounce, so we've got 2. Okay, perfect. And determine end behavior, we've got down to up. So does that tell you that your A should be negative or positive? Positive, perfect. So I'm just going to write positive A. So now I'm going to just take all of that and I'm going to combine it. We know it's positive A, so no, no, and no. And then we have minus B plus C and plus D. If we write that in the 0 form, we've got x plus B, x minus C, and x minus D. So we would know that it's this one right here. Positive A, x plus B squared, x minus C to the 1, x minus D squared. Okay? Perfect. T of x. Polynomial division. All right. You've got, does any of you guys do box division? No? Perfect. We don't have to worry about that one. There's 3 different types of division, and you've got long division right here, synthetic division, and also box division. Some people do that, but that's not a common one, so we're not going to go over that at all. Polynomial division is just like long division. Oh, wait. Long division is set up just like if you're doing normal numbers. So if we've got 53 divided by 5, for example, we're going to do 5 into 5 once, and you just do this entire thing. That subtract, a lot of people forget to do to make it negative there, but remainder 3. So that would be if I was just doing normal integers. Now, long division with the polynomials is the exact same thing. You just have to multiply and see how many times it can go into it. The remainder is whatever cannot be divided right here. You can do remainder 3. You can also do remainder 3/5, and that same goes with polynomials. You can do remainder over the quotient or the divisor. Okay, you can do the remainder over the divisor for another way of doing it, and that would be plus. Synthetic division can only be using when dividing by a 0. So it has to be in this form right here. It can't be 2 zeros. It can't be an x squared, any sort of quadratic or more. It has to be just 1x minus something. And you would set that up, let's see, with 0 and coefficients. The problem doesn't, there's not an example problem for synthetic, so I'm just going to do a quick example one right here so that we can see kind of how it goes in case you want to use it. Let's say we want to divide x squared plus 2x plus 2. Yeah, no, I'll do 3. Sorry. Perfect, 3. And then I'm going to do divided by x plus 2. Okay, so right here, x plus 2 is in that form, so we can use it. That's how you know. And then you want to take your c and you want to do the opposite of it. So you would want to do x plus 2 equals 0. And then you can bring the 2 on both sides of it. X equals -2. That's how you know it's the negative. And then you're going to set it up like this. You're doing the coefficients. That's what you want to pay attention to. So x squared, the coefficient is 1. For x, the coefficient is 3. And the constant, the coefficient is 2. And then right here, you want to take that -2 and you want to put it right here. Kind of like, I don't know, it's just like off on the shelf. First step is always to bring this one down. No matter what, you bring the first term down. And then you multiply. 1 times -2 is -2. 3 plus -2 is going to be 1. 1 times -2 is -2 as well. 2 minus 2 is 0. So when that is a 0, then you know that this works as a 0. So you can use this if you're not sure if it's a 0, because if your remainder is not 0, then what you just tried doesn't work as a 0. So you want to try different ones. You can also use it when you know that it's for sure a 0, because then you can get it in a simplified form, which this one would be x plus 1. So you just kind of like take, this one was x squared, x and constant, and then you just take 1 away. If you start with x squared, you take 1 away, and it's going to be x to the 1, and that's how you know that one's x to the 1. So you just do 1 power lower. But yeah, that's just an example for synthetic. I don't know if you guys like it. I like to do synthetic a lot, as much as I can, but you can't do synthetic if you don't have it in this form. So that's an important thing to remember. Perfect. Use polynomial division to write the rational expression as a polynomial in descending powers plus remainder. So this one, since we're in the form x squared plus 1, you cannot use synthetic division because it's not, if it was x plus 2, you could, but x squared plus 2, you can't, because it's, you can factor it even further. It's not a full 0 yet. So in that case, we're going to do long division. That's the other option that we have. So 2x cubed minus 6x squared. I'm just going to do 0x plus 1 divided by x squared plus 0x plus 2. So just remember those empty spots if there's nothing there. And then we're just going to we're going to put the whole thing in. So first, just looking at the the x squared and the 2x cubed, then x squared can go into 2x cubed 2x. times, and then you're going to multiply that, 2x cubed plus 0x squared plus, 4x. And then I'm going to do the whole thing by negative right there. That cancels out. This becomes minus 6x squared. And this one becomes minus 4x. Okay, minus 4x because of the negative. And then bring the 1 down. Put that one into it. You've got minus 6. And multiply that out. Minus 6x squared plus 0x minus 12. And multiply out by negative again. That cancels out. Negative 4x. And then plus 13. Remember, in this before, the remainder is whatever cannot be divided anymore. So this can't be divided anymore because it's less. So plus a remainder, then your remainder is going to be this over your divisor. So you've got plus negative 4x plus 13 over what you started with, x squared plus 2. So that would be your final answer, like that. Perfect. Just make sure that's a full fraction, and those ones are whole numbers. Any questions with that? Got it? Real zeros of polynomials. Real zeros of polynomials, and this one is the rational zeros theorem. So the rational zeros theorem, if you ever hear about that, then you just want to think of PQ, okay? So that one's going to be plus or minus P over Q, where P is all of the factors of the constant, and Q is all of the factors of leading coefficient. So you take the very last term, very last term, and break that into all the factors, and the very first term, and break that into the factors, and put it into this fraction. Okay, and you want to take all of the different combinations of it. Once you have a whole list of them, some of the time it'll be a really long list, some of the time it'll be like 4 different things to plug in, then you can plug it into your polynomial, and if you get a 0, then it's a 0. So it's kind of confusing because the word 0 is like one of the x-intercepts, but it also, you get 0. So it's a lot of zeros in this part, but if you plug it in and you get 0, then it's 0. You can also try it with synthetic division, which is what I did before. If you get the 0 as a remainder, then it's also 0. Either way, you have this whole list, and you just kind of want to guess and check at this point. Your first step is guessing and checking. And then after you have that, then you can divide it down, and you'll simplify the polynomial so it can be something a little bit more manageable. And if it's in an x squared point, then we can do what we're used to. And you can just look at it, factor into 2 of them, and if you can't look at it and factor it, then you can do quadratic formula. Quadratic formula is always kind of the thing to fall back on if you're at that point. Okay, perfect. So let's try this out. Use rational zeros theorem to find potential rational zeros. So right here, you want to take the constant. You've got 1. The factors of 1 are 1 and 1. So we're going to do 1 over all of the factors of 2, which are 1 and 2. And we want to do plus and minus. We want to always remember the negatives in there too. So that we just did the entire rational zeros theorem, which was super quick. That's all you have to remember. And now let's write that into a list. We've got the list of 1, 1/2, -1, and -1/2. So those are 4 potential values that could be 0. Let's just see if they are. Testing the values, then a lot of the time, good bet to just do 1 and -1 because those are kind of easier ones to plug in. So you would do 2 times 1 cubed minus 1 squared minus 2 times 1 plus 1. That we've got 2 minus 1 minus 2 plus 1. Perfect. That would equal 0 because those all cancel out. Okay, so already your first check, obviously we have good odds here because you only have 4, but our first check got a 0, so we know that x minus 1 is a 0. That's what that tells us. After finding 1, 0, you can factor, use synthetic division, or test more values to find the rest. So, do you guys want to factor, or use synthetic division, or test all of values? Because if you want, you don't have to do any sort of division, and you can just plug and chug the entire thing. And then once you have 3 different zeros, then you are done. You have all of your zeros. What would you guys like to do?
You gotta rather divide.
Divide? Okay.
You do that more often.
Synthetic or long division?
I don't even know how to do synthetic division. I just do long division.
Okay, do you guys want to practice synthetic or no? No, that's fine. If it's not broke, don't fix it. Okay, let's do 2x cubed minus x squared minus 2x plus 1, and we're going to divide it by x minus 1, which we just found out is 0. Okay, x minus 1, or x can go into 2x cubed, 2x squared times. Multiply that, we've got 2x cubed minus 2x squared. Subtract. Negative 1 plus 2 is just going to be positive 1x squared minus 2x plus x. Now I'm going to multiply by the negative. Cancels that one out. Negative 2 plus x is negative x plus 1. And then x minus 1 can go into... x minus 1 can go into negative x plus 1, negative 1 times, and then you've got negative x plus 1. And that subtracts to get 0. Okay, so after dividing, then we know that 2x cubed minus x squared minus 2x plus 1 can be rewritten as x minus 1 times, and then your quotient, 2x squared plus x minus 1. Okay? That's what we just got from dividing. So we're just breaking it down more and more and more. Now we have it in a quadratic form. Thank goodness. So now we've got 2x squared plus x minus 1. Is there anything looking at it that you know we can do, or should we do the quadratic formula? But I say let's do the quadratic formula. Because everyone has their own preferences for factoring, but quadratic formula is a safe bet. So we're just going to do minus b, so minus 1 plus or minus the square root of b squared minus 4 times 2 times negative 1 all over 2a, so 2 times 2. Let's simplify that to get 1 plus 8 over 4. 1 plus 8 is 9. Square root of 9 is 3. So we've got negative 1 plus or minus 3 over 4. And now we've just got two options. Negative 1 plus 3 over 4 and negative 1 minus 3 over 4. Negative 1 plus 3 is positive 2 over 4. So it's going to be, we've got 2/4 as an option. I'm going to do 2/4. And negative 1 minus 3 is negative 4 over 4, negative 1. So those would be our two, what the quadratic formula got us. 2/4 can be simplified to 1/2 as well. Perfect. And now, from there, then we are just going to write it in this same form. We've got x minus 1. This is telling you over here, then you know that x equals negative 1. So you're just going to add a 1 on both sides, and that would give you x plus 1 equals 0. So you know that x plus 1 is there. And then 1/2, you're going to do the same thing, but since we're dealing with a fraction, then you can't just subtract the 1/2. This is the big thing to remember. Don't just subtract the 1/2. You want to multiply by the 2 on both sides. So times by 2, and then you'd have 2x equals 1, and then you subtract the 1. So right here, you would have 2x minus 1, and that equals 0. Anyway, so I just took these two zeros that we found from quadratic formula and I rewrote them in this form. You also know that you want 2x minus 1 because if you're multiplying all of it out, then you can kind of quickly check if you factored it right by looking at all of these first terms. You've got x, x, and 2x. If you multiply all of that out, you get 2x cubed. Oh, perfect. That's what we started with, 2x cubed. And then you multiply all of these out. -1, +1, and -1. You have -1. Oh, did we do it wrong? Oh, what the, yeah, -1 times -1 is positive. Sorry, what the, and we have a +1. Okay, so if you want to check, then you do all of your first terms multiply and last terms multiply. These middle ones don't actually matter for checking. As long as the first two, the first and the last work, then you got it good. Okay? And then we've got 1, -1, and 1/2. Sorry, I keep doing the wrong thing. We did the full factored form. If it just asks for the zeros, then you can write it in that form. But we did the same work either way. It's just the way that they ask for it. Oh, well, that would be nice. Sorry if that was way too crowded. I should have moved on. Any questions with that? Okay. Are you good?
Yep.
Perfect. Sorry, I kind of took a while for that, but.
That's okay. Okay, so now we're going to talk about the fundamental theorem of algebra. So we have the definition here. If f of x is a polynomial with real number coefficients and a leading term of a sub n, x to the n, then f of x can be written in the form f of x equals a sub n, the leading coefficient, times by the factored form, which is x minus c1, x minus c2, all the way to x minus cn. Where c1, c2, and cn are complex numbers and not necessarily unique. This means pretty much that if we have n x to the n, then we're going to have that many zeros in factored form. But they're not necessarily unique. So that means that some terms could be x minus c, which is the same as x minus c squared. The other thing to note is that complex numbers are always in the form of a plus bi, and sometimes b can equal 0, which means that it's just a, which means it's just a real number. But it can be either a real number or a complex form. Polynomials of degree n have precisely n factors of the form x minus c, so we can completely factor every polynomial. And the sum of all multiplicities of all the zeros of polynomial is equal to the degree. So that pretty much means if we write everything out, x minus c1, x minus c2, x minus c3, right? Eventually you're going to get x times x times x is going to be x cubed, and plus whatever. And that just means that that's kind of you go back and forth. So the degree of the leading coefficient is how many factored polynomials you can have. Again, they can be the same and have multiplicity of greater than 1. Any questions with that so far? Okay. So, problem 7. We're going to use the graph to determine how many rational zeros there are for the function. So first of all, we're going to note we have this function here, and the leading coefficient, the polynomial of that is 5, right? So that we have degree is 5, which means that we're going to have 5 zeros. So we have one here, one here, one here, one here, one here, right? 1, 2, 3, 4, 5. So that matches up with that. So we're going to use the rational zeros theorem that we just learned to determine which of these are rational and which are irrational. So if we go back, we have our p is going to be all the factors of 14. So you have plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. Our q values come from our leading coefficient, which is just 1, so it's just going to be plus or minus 1. So our list of possible rational zeros is going to be plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. So we can compare these possible rational zeros to our graph Do we have anything that looks like -2 to -3? Not really, right? That's a decimal number. We don't have any decimals in here. However, we have -1. So looks like x is equal to -1. Because that's right here. We have 1, which is also right here. So that matches here. We have 2, which matches right here. And we have 2 point something, which is also not in our rational zeros list. So we have our set of x's that are zeros, that are rational, which is -1, 1, and 2. So we have 3 rational zeros. Any questions? Okay. Now, we can determine how many rational zeros there are for the function. So if you remember, these 3 were all rational. But we also have these 2 zeros right here. So we know that there is a multiplicity of 5, right? So that means that there's 5 total zeros. They can range from being rational, irrational, or imaginary. So we know that there are 3 rational, and there are 2 other zeros that cross the x-axis, so they're not imaginary. So that means that we have 2 irrational zeros. And those are right here and right here. Okay.
So is it just going to ask you how many there are, the zeros, not the actual zeros themselves?
Yep. On the, I believe on the CBE it'll ask you it may ask you what rational zero it is, but if it asks you how many, you're just listing out the number of how many it is. And yeah. One thing, I guess I'll talk about that later if we don't mention it, but there is something with this too. Okay. Now we're going to determine how many imaginary zeros there are. So we know that any zeros not rational or irrational must be imaginary. And we know that imaginary zeros are where the graph kind of like goes like this, right? So there should be a 0 here, but it doesn't actually cross the x-axis. And so we have points that are imaginary as our roots. Because we know the degree is 5, and we know that there was 3 rational and 2 irrational, that leaves us with 0 imaginary, right? 3 rational, 2 irrational, sums up to 5, which leaves us with 0 imaginary. Any questions with that? Okay. So 0 imaginary zeros.
If you're trying to find the imaginary zeros, I don't know if that's what this question is going to be. You just put it into the quadratic formula, and that'll...
Yeah. So we'll get into that. If you're trying to find the values, what your question is, of like the imaginary zeros? Yeah. So you'll have a certain set of rational zeros, maybe a certain set of irrational zeros, and then that will kind of leave you with if you divide that from the zeros, from the whole function, then that will leave you with a quadratic that then you can solve for the values of the imaginary zeros. Yep. In this problem, we're actually going to kind of do the reverse of that. So we're given the imaginary zeros, and we're trying to now find the rational and irrational zeros. Also, one thing to note, I believe on the test, it asks, when you have, say, something that bounces off the x-axis, it has a multiplicity of 2, but it only counts for 1 0. So when you're adding up for multiplicity, you need to account for it has 2 for that. But when you actually put it as the answer on the test, when you actually have zeros, there is only 1 0 there. So that's an important thing to note. So going back to this question now, we're going to find all the zeros of this polynomial. And it gives us a hint, which is very nice. It gives us a 0, which is the square root of 2i. So when we have the square root of 2i, we know from a theorem that we learned in class that if one of the zeros is the square root of 2i, we must also have the complex conjugate of that 0. So we also know that negative square root of 2i is also a 0 of this function. So we know that they come in pairs. So we know that x minus the square root of 2i times x plus the square root of 2i are two of our factors that go into our function. And what we can do with this is we can multiply them together and then divide that by the whole function to find the remaining rational and irrational zeros. So if we multiply this together, we're going to get x squared plus square root of 2ix minus the square root of 2ix. Sorry, that was bad. 2ix. And then we're going to get minus the square root of 2 times the square root of 2 times I squared. And this implies these add to 0. These multiply to 2. I squared becomes negative 1, right? So we're left with x squared. That becomes positive plus 2. Is everyone okay with that? So we have the two imaginary zeros multiplied together, and then what we can do is we can use polynomial division. So we can set that up. We can do x squared plus 2. Put that the rest of the term in here. X squared minus 4x cubed minus 3x squared minus 8x minus 10. So going with what we've already learned. So we have x squared is the first term that we must multiply. So you multiply that, you get x to the fourth, and then 2 times x squared is going to be 2x squared. And make sure you put that underneath the column that it pertains to. Then we're going to subtract that from this, and we're going to get that these two subtract to 0. This becomes a negative, which means it's negative 5x squared. We're going to pull this down, so it's negative 4x cubed, and then we're going to write the rest of the terms. Okay, the next time we're going to have negative 4x. So negative 4x times x squared is negative 4x cubed. Negative 4x times 2 is negative 8x, which means that we subtract this from that, we're going to get that these add to 0. These also add to 0, which means we're left with negative 5x squared minus 10. And then our last term will be negative 5. So we're going to get negative 5x squared. Negative 5 times 2 is negative 10. And if we subtract those, that will subtract to 0, which is good. If you ever don't get 0 with this, that means that you've done some sort of something wrong, because if you divide a function by its factor, it should always equal 0. So we got 0, which means we did it right. So now we have x squared plus 2, and then we're multiplying that by x squared minus 4x minus 5. And this is actually a factored form of p of x. So what we can do there is we can factor the other one. So you have x squared plus 2. And then we can factor this down. Negative 5 and 1 multiply to get negative 5 and add to negative 4. So we can do x minus 5. And we can do x minus 1. Plus 1. And then that will be the factored form of p of x. So then our list of zeros will be our two complex zeros, imaginary zeros. Sorry. So we have square root of 2i. We have negative square root of 2i. And we take the opposite of these, so we have 5 and negative 1. So there will be our solution. Any questions with that? Okay. So now we'll be going on to the rational function graphs. So a rational function is any function where the output can be defined by dividing a polynomial by a polynomial. So in other words, they're a fraction where the numerator and denominator are both polynomials. So you have some sort of an x to the n plus ... over what the other, like bn x to the m or something plus ... So they're both going to be polynomials. So you have a polynomial in the numerator, polynomial in the denominator. And these, to graph them, we need to look for certain things. They're going to be holes, asymptotes, x and y intercepts, and I believe that's the list. So first of all, with holes, rational functions have holes for any input that is 0 of both the numerator and the denominator. So they divide to 1 in factored form. So you find the wholes by taking the factored form of the numerator and the denominator, dividing, if there's any factors that are the same, you can divide those to 1, and then you plug that value of the factor back into the reduced form to find the y value. And we'll do an example of this. But an example would be kind of just like write this out. X minus c, x minus b, and then the bottom might have x minus a, x minus c, right? These two divide to 1, which means that the reduced form is x minus b over x minus a, and we're going to have a whole at x equals c. And then we plug c back into for x, and that's how we define the y value. Vertical asymptotes. You can find the vertical asymptotes by finding the zeros of the denominator in the reduced rational function. So if we take the example function we already had, x minus b over x minus a, the vertical asymptote is going to be where x equals a. And that's kind of something where it's going to be that, and the function is probably going to go and either kind of follow it in some sort of way. That's going to be the end behavior. It's going to follow the vertical asymptote. So when the denominator is 0, the function is undefined, which means that there's not going to be any x values that satisfy that are real numbers. And then, yeah, what I showed above is when the function goes to positive or negative infinity as the x values approach the asymptote. The end behavior is a horizontal asymptote. So there's a couple types of horizontal asymptotes and how to determine them. So if the degree of the numerator is less than the degree of the denominator, so we'll say that x to the n, and then there's a greater in the denominator, then the horizontal asymptote is at y equals 0. And if we think about this as it like you get a really, really big x number, the denominator is going to be very, very much bigger than the numerator, which means if you divide a small number by a really big number, it's going to go to 0. So we'll have a horizontal asymptote at y equals 0. If the degree in the numerator is equal, so you have x to the n over x to the n, and we'll have put coefficients of a and b, then the horizontal asymptote is found by dividing the lead coefficients. So it'll be at y equals a over b. So we're going to take the leading coefficients of both of those, divide them if the degrees are the same. And the end behavior is oblique or slant asymptote if the degree in the numerator is exactly 1 greater than the degree in the denominator. And that kind of looks like something like it's going to be a line. So you have some sort of line, and then the end behavior of the graph will kind of get really close to the line, but it will never cross it. And then finally, our zeros. Zeros are anything in the numerator that go to 0. So if we go back to our original example that I had written down, x minus b over x minus a, we ignore the denominator and we solve that x equals b is a 0 of the graph. Because if you plug in b minus b is 0, 0 divided by anything besides 0 is 0. So we're going to do an example. We're going to find a hole first of all. You have a question? Yeah.
Sorry, going back super quick to the horizontal asymptote. If it's a slant asymptote, how do we find that slant again?
Yeah.
You divide something.
Yeah. So we're going to divide the denominator. To find a slant asymptote, we're going to divide the denominator by the numerator. So we're going to perform long division. And
That's just it.
yep, and we'll do an example of that later. So perfect. Okay. So does the following graph contain any holes? And what are the coordinates for the holes? So first thing we do is we factor. So our numerator can factor to x plus 2, x minus 1. And our denominator can factor to x minus 2, x minus 1. So if we notice, we have a term in the numerator, x minus 1, which is the same as the term in the denominator of x minus 1. So those divide to 1. our reduced form is x plus 2 over x minus 2. And we know that we have a whole at x equals 1, which is the solution to that factor that was canceled out. We found the common factors, we reduced, and now we're going to plug in x to the reduced form. So we know that the y value is going to equal to 1 plus 2 over 1 minus 2, which is equal to 3 over negative 1, which is equal to negative 3. So we have a whole at the coordinate 1, negative 3. Any questions with holes? Okay. Okay, so now we're going to find vertical asymptotes. So if we remember the reduced form, it was x plus 2 over x minus 2. Wait, this is a different equation. Never mind. Let me erase that quick. Okay, so now we have a different equation here. So we're still going to factor. One thing that we can do here is we can factor out 5. So that leaves us with 5, and then in the parentheses x squared plus x minus 6. And then below we can factor out a 2x, which is going to leave us with x minus 2. And then this also is equal to 5. We can factor even further. We can go x plus 3, x minus 2, and we still have the same in the denominator, x minus 2. So we notice, first of all, that we have a term in the numerator that's the same as the denominator. So that divides to 1. And we have a whole at 2. X equals 2. So we have a whole at x equals 2. So our reduced form is going to be 5x plus 3 over 2x. And then we find the zeros of the denominator. So the way we do that, we set 2x equals 0, which means that we have a 0 at x equals 0. And that will be our vertical asymptote. At x equals 0. Now, does this graph have any horizontal asymptotes? So if we remembered our reduced form, 5x plus 3 over 2x. Our horizontal asymptotes comes from looking at the degrees of the polynomials, first of all, right? So the degree of the numerator is going to be 2, and the degree of the denominator is going to be 2 as well, which means that we look at the lead coefficients. And this is the same in the reduced or our original, right? So if we look at that, we know that we have a horizontal asymptote at y equals 5/2. Any questions with that? Okay. So, and then where does the graph cross the x-axis? So for this one, we will need a reduced form because there might be a hole. And so we have 5x plus 3 over 2x. And we know that we have a whole, we have a x-intercept. And we only look at the numerator, right? So we can kind of ignore the denominator. Set that equal to 0. We only have one factor, which means that we can look at only the factor as well, because we can divide 5, and 0 divided by 5 is 0. And then we get that x is equal to negative 3. So we have a 0 at negative 3, 0. Any questions there? Okay. And then we're going to plot the horizontal asymptotes, vertical asymptotes, and zeros. So if you remember, we had a horizontal asymptote at 5/2. So that would be 2.5. So we have one right here. And then we have a vertical asymptote at at 0. And we have a 0 at -3. And while it doesn't ask us to graph this, we can kind of tell that we know that the graph is going to come somewhere and going to go toward that asymptote. It's going to cross, and it's going to come toward this one. We have a hole, and if we plug that one back in to 5, we know we have a hole at 2. And we plug that in 2 times 2. We get that it's 5 times 5 is 25 divided by 4, which is up here. And we have the same, kind of comes up here, and that's going to go and approach here. So that'll be our graph. Any questions with that? Okay. So now we're going to do a similar thing with another example with another equation. So this time we're going to solve for vertical asymptotes first. So we're going to reduce this. So we have 2 we can take out, and actually an x as well. All the terms in the numerator have an x, 2x. So that leaves us with x squared plus 2x minus 3. And the denominator reduces, or we can factor it out to be x plus 2, x minus 1. This reduces, or we can factor further to be 2x, x plus 3, x minus 1. And then our denominator stays the same. X plus 2, x minus 1. And we notice here we have another factor that can reduce to 1. So we have a hole at x equals 1. And our reduced form is 2x, x plus 3, over x plus 2. So our vertical asymptotes, we look at the denominator, right? We set the denominator equal to 0. And we have a vertical asymptote at x equals -2. For our next one, got that down? Okay. For the next one, we're going to look and see if it has an oblique asymptote. So here we'll be answering your question. So we can notice the degree in the numerator is 3, and the degree in the denominator is 2, which means that the numerator has a degree of 1 more exactly than the denominator. So we looked at the degree. Now we're going to divide the numerator by the denominator and ignore the remainder. We can do this either from the original function or from the reduced function. And the reduced function is a little easier, so I'm going to do it with that. So you have x plus 2 is divided by, so you have 2x, x plus 2, sorry, x plus 3, divided by x plus 2. If we have 2x squared plus 6x. So we're going to multiply 2x to get 2x squared plus 4x, and then we can subtract that. Those subtract to 0. 6x minus 4x is 2x, and then we have plus 2, and then we can do 2x plus 4x, and then we have 4, right? -4. And we have a remainder here of 4 divided by x plus 2, but we can kind of ignore that remainder, and we have an oblique asymptote at y equals 2x plus 2. So any questions? Does that answer your question? Okay. So, got that oblique asymptote. Now we're going to find where does it cross the x-axis? In other words, what are our zeros of this function? So if we go back to our reduced form, which is 2x, 2x, x plus 3, divided by x plus 2. We're going to set the top 2x, x plus 3 equal to 0. And note that we have two factors, which means that each of these can also equal 0. And we have an x equals 0 and negative 3 is where our zeros are. If we write that in coordinates, it would be 0, 0, and negative 3, 0. Any questions with that? Okay, so now we have our x-intercepts, and we can now plot our function with all that stuff. So we have the slant asymptote, which was at 2x plus 2. So we know that that's going to cross at 2, and it's going to go up 2 over 2. So it's going to cross here and here. So if we just draw a line, and it's going to come down this way as well. And then we have a vertical asymptote, which was at x equals negative 2. So we can draw this one right here. And our zeros we're at 0, 0, and negative 3, 0. So we have 0 zeros here and negative 3 zeros here. So with that, we know that we can graph it. This is going to go up and kind of approach here, and it's going to go down, and it's going to approach this vertical asymptote. And from this side, it's going to go approach here, and it's going to come, oops, if I can draw, and it's going to approach that slant asymptote. If you're ever confused or don't know about where the graph goes, you can always plug in numbers. Here they were given to us because we already knew the zeros, but you can always plug in numbers and kind of see where the graph lands. So, any questions with graphing with vertical or horizontal or slant asymptotes or any of that? Okay, that leaves us to the end of the review. Is there any questions with anything in the review? Okay, so if you need any more help, if you'd like to go over practice problems specifically, you're welcome to come to the AMLAC. There's always tutors. You can come to your recitation leader's office hours or professor's office hours, and there's always help. So we hope you do good on the CB3. Yeah, good luck.
Yeah, good luck.